In class 77, we looked at reflection, refraction, dispersion, diffraction, and polarization. Polarization is not a topic you need to know for the Regents exam, so it's not one we're going to cover in this class. I know some classes got to it, some didn't. If you didn't get to it, don't worry about it as a topic. So looking at reflection, light approaches a mirror at an angle of 25 degrees with respect to the normal. Label the 25 degrees on the diagram below. So it's really important. The hardest part about law of incident, or excuse me, the law of reflection is identifying the angle of incidence and the angle of reflection. So this right here is our angle of incidence, theta I. That's 25 degrees. It's always measured with respect to the normal, which is this dotted imaginary perpendicular line perpendicular to the surface of the mirror. Our angle of reflection is right here. That's theta R. Don't get that confused with refraction. That's also 25 degrees. Our normal line is right here. So what's the angle between the incident and reflected ray? So that red line is the ray of light. It comes in at an angle of 25, leaves in an angle of 25. So that total angle there is 50 degrees. It's as easy as that. So the law of reflection tells us that the angle of incidence, some people say angle of incident, I'm not really sure exactly which one it is, but incidence, incident, the same thing, equals the angle of reflection. Please don't say refraction. Okay, when we get to refraction, some students get confused and they think the angle of incidence equals angle of refraction. That is not the case. Okay, so just watch out for that. That equation right here is on your equation sheet though, so you do have it on hand. So we get into refraction a lot more in a couple classes. So all you have to know in this class is that refraction is when light changes direction when traveling from one medium to another. I think this image of the glass does a really good job of showing, the one on the left, does a really good job of showing that light does not take a straight line path through a piece of glass. And this image of the water and the glass is a pretty classic picture of refraction. So dispersion is an application of refraction. So this image here is, you might have seen it like on Pink Floyd's album Dark Side of the Moon, shows that white light spreads into all the colors of the rainbow. So when white light goes from air to glass, the different colors refract different amounts. So if you actually notice on your reference table, it mentions that the indices of refraction that are given are for yellow light, because that's kind of like the middle color and the middle amount of refraction. But all colors actually refract a little bit differently, so there is a different index of refraction for every color. That's beyond the scope of this class, though. Not really something you need to know aside from its application in dispersion. You just have to know what dispersion is. So looking at the image here, violet refracts the most, and it looks like red refracts the least. Okay, so you have violet changes direction the most from the white light, and red changes direction the least. This unequal refracting causes white light to spread into a spectrum. We call this dispersion. And we checked out how to make rainbows and stuff in the simulation here. You could check that out. So just like last unit, light waves, just like sound waves, do diffract. Now, the bending of light as it passes the edges of a barrier is called diffraction. Now we use the simulation from the previous page to, or a different simulation in class to show that how wavelength and how opening size affect diffraction. We found that as wavelength goes up, diffraction goes up. So that's why we use radio waves to transmit information, because since they have the longest wavelength, they're really good at bending around objects and obstacles like buildings and stuff like that. We also found that as the size of the opening goes down, diffraction goes up. Okay, so some people said that was like an inverse relationship. That's a fine way to think of it. And they said that wavelength to diffraction is a direct relationship. You can think of it that way. That's just fine. In polarization, this was an extra topic. We're not really going to go into it, but we checked out some polarizing lenses in class. Just looking at the practice questions down here. Which diagram represents diffraction of wavefronts as they encounter an obstacle? So these two show reflection, 3 and 4. 2 shows waves going past an obstacle but not changing direction. Remember, when obstacles pass the edge of a barrier, they kind of bend or kind of change direction as they encounter it. That's why when it goes through a slit, it kind of spreads out in all directions when it goes through past those edges. For this one, the diagram below represents a ray of light reflecting from a plane mirror. The angle of reflection for this ray of light is, a lot of people might choose 20 for this one. Watch out, it's 70. This is just checking if you know the difference between incident and reflection. So just be careful of that, all right? This is the angle of reflection. This is the angle of incidence, okay?